Okay, today we're going to talk about solving logarithmic equations. First off, this is what we did yesterday, this warm-up here. If we were looking for the domain of this first 2 log base 3 of x minus 4 plus 3, remember that this has been moved to the right 4, and it has been moved up 3. So this right here, as far as the domain is concerned, it looks like this. And it has a vertical asymptote at x equals 4. So my domain is from 4 to infinity. Both of those are soft brackets. My range is going to be all real numbers, or from negative infinity to positive infinity. My asymptote is at x equals 4. My x-intercept is when y is equal to 0. So if I said that 0 equals 2 log base 3 of x minus 4 plus 3, subtract 3 from both sides, I have negative 3 equals 2 log base 3 of x minus 4. Divide by 2. So I have to isolate that logarithm first. So I have negative 3 halves equals log base 3 of x minus 4. And now that I've isolated the logarithm, I can rewrite this as an exponential. So I have 3 to the negative 3 halves equals x minus 4. And 3 to the negative 3 halves. Let's think about what's happening here. So I've got 3 to the third, right? The 1/2 of that is the square root, and then negative is 1 over that. So this would be 1 over 3 halves. This doesn't say that it needs anything specified, so like to the nearest 10th or anything like that. So I'm going to add 4 to both sides. So my x-intercept is at 4 plus 3 to the negative 3 halves. So that's my x-intercept is at 4. Oh, whoops, sorry. Plus 3 to the negative 3 halves, comma, 0. My y-intercept's a little bit easier to find. That's when x is equal to 0. So that would be at 2 log base 3 of 0 minus 4 plus 3, or 2 log base 3 of 4, negative 4, sorry, plus 3. You can't simplify log base 3 of negative 4. So one thing to think about here is as far as the y-intercept is concerned. First of all, if you look at our picture, right, here's my coordinate plane over there. So it doesn't actually touch the y-intercept by looking at the x-axis, or if you look at the coordinate plane. But also, I can't have a negative here. That would make this undefined. So as far as the y-intercept is concerned, there's none. For this second one here, the negative natural log of x plus 2. So this looks like this here, with my coordinate plane like this. And I have my vertical asymptote at x equals negative 2. That's where my asymptote is, based on that 2 right there. So my domain is from negative 2 to infinity. My range is still all real numbers. And my x-intercept. So if I was going to find my x-intercept, I would say that 0 equals negative natural log of x plus 2. Okay. Divide both sides by negative 1, but 0 divided by negative 1 is just 0. equals the natural log of x plus 2. And I've isolated my logarithm, so I'm going to rewrite it as an exponential. So I've got e to the 0 equals x plus 2, or anything to the 0 power is 1. And then if I subtract 2 from both sides, negative 1 is x. So my x-intercept is at negative 1, 0. And then my y-intercept is when x is 0. So I have y equals negative natural log of 0 plus 2, or negative natural log of 2. And you can leave it just like that because that's the exact answer. So you would have 0, comma, negative natural log of 2. So today we're going to talk about solving these equations. So you're going to isolate the logarithm, rewrite it in exponential form, solve for x, and check for extraneous solutions. So this is the isolation of the logarithm in this first one. This is the isolation of the logarithm in this second example here. So the first one's actually already been isolated. So the next idea is I'm going to rewrite this in exponential form. So this is going to be, remember that there's no number here, so it's a 10. So this would be 10 squared equals x minus 3. 10 squared is 100. And then add 3 to both sides. And so 103 is x. Now, if I were to plug 103 back into here, I would end up with the log of 100, and that's okay because that's positive. So that is not an extraneous solution. In number 2 here, I have to start out by isolating my logarithm. So I'm going to subtract 5. I have 4 log base 3 of x equals 2. Divide by 4. And so log base 3 of x equals 2 divided by 4 is the same as 1/2. So then, if I rewrite that as an exponential, I have 3 to the 1/2, or the square root of 3, equals x. So the square root of 3. If I were to plug that in, it would not be an extraneous solution, right? Because that's positive. The square root of 3 is positive. This next one, my logarithms are already isolated in both of these, okay? So I'm going to rewrite them both as exponentials. So first, 2 to the negative third equals x minus 4. 2 to the negative third, that's the same as 1 over 2 to the third, or 1/8 equals x minus 4. And then if you add 4, you would have 4 and 1/8. Or 33 over 4 is x. And if I were to plug that in, I would get a positive number in here, because 33/4, sorry, this should be an 8, not a 4. 33/8 minus 4 is just that 1/8. So it's still positive. Next one. It's already isolated, so I'm going to rewrite this as an exponential. So I don't have anything here, but it's a natural log, so this would be e to the 0 equals 10x minus 4. Anything to the 0 power is 1, so this is 1 equals 10x minus 4. Add 4. So 5 is 10x. Divide by 10. And 5 over 10 is 1/2. If I were to put this back into the equation, 10 times 1/2 is 5, and 5 minus 4 is 1. So that is not an extraneous solution. All right, this one's a little bit different. So let's use our logarithm properties, right? The log of A plus the log of B is equal to the log of AB. And I'm going to use that here, where I've got the log of A is the log of x, and then the log of B is the log of x plus 3. And I can write this as a single logarithm now. So I've got log of x times x plus 3 equals 1. That's an isolated logarithm, so I'm just going to rewrite this as an exponential now. So it's got a base of 10, so 10 to the first equals x times x plus 3, or 10 equals x squared plus 3x. I notice that this is a quadratic, so I'm going to have to set it equal to 0 and solve. So I subtract 10. Ideally, I can do this by factoring. That's my personal favorite, but maybe you like quadratic equation better. This is factorable. This would be x plus 5 times x minus 2. So my solutions would be -5 and 2. And let's make sure that neither of those are extraneous solutions. So if I were to plug in -5 here, I would be taking the logarithm of a negative number, so this does not work. But 2 works for both. I would not be taking the logarithm of a negative number. Next, same idea here. So the property that I'd be looking at here is the log of A minus the log of B would be the log of A over B. So I'm going to reuse that, where the log of A is this log base 6 of x, and the log of B is log base 6 of x minus 5. So to rewrite this as a single logarithm, I would have the log base 6 of x divided by x minus 5 equals 2. I've now isolated this logarithm, and I can rewrite it as an exponential. So I have 6 squared equals x divided by x minus 5, and I'm going to start to solve this. 6 squared is 36, and I'm going to get rid of this fraction. I'm going to multiply both sides by x minus 5. When I do that, I get 36x minus 5 times 36, which is 180, equals x. It's a little bit easier to handle now. So now I'm going to subtract 36x. So I have negative 180 equals negative 35x. Divide by negative 35. And I get 180 divided by 35, which is it's a fraction. You should have an exact answer. If you do that in the calculator, you get 5.14 or something, right? So as a fraction, it's 36 sevenths. So you've got 36 sevenths is x. Now to check to see if that's an extraneous solution, 36 sevenths obviously in that first one, and here would be okay. And then 36 sevenths minus 5 is still a positive number, so this does work. It's not an extraneous solution. Okay. Here I've got logarithms on two sides. Now, there's a couple of ways that you could do this. One way that you could look at this is you could subtract. So watch these so that you can kind of pick which way you want to do better. So you've got log base 8 of 4x minus 9. And if you subtract that from both sides, you end up being able to use that property of logarithms. But I want you to see what happens here. So if I rewrite that as a single logarithm, I have log base 8 of x plus 6 divided by 4x minus 9 equals 0. Rewrite that as an exponential, so you have 8 to the 0 equals x plus 6 divided by 4x minus 9. Anything to the 0 power is 1. So 1 equals x plus 6 divided by 4x minus 9. And get rid of that fraction. Multiply both sides by 4x minus 9. And you get 4x minus 9 equals x plus 6. And if you look back at the original question, right, I have x plus 6 equals 4x minus 9. So you actually can just skip all of that, but that's why that works. And just say that x plus 6 equals 4x minus 9 because the log base 8 is equal to the log base 8. So you can just kind of get rid of it there. But if we solve from here, I'm going to subtract x. So I have 3x minus 9 equals 6. Add 9. So 3x equals 15. Divide by 3, and x is 5. We want to make sure that that's not an extraneous solution. So if I go back up here, if x is 5, here I would have 11, and here I would have 11. I know that my answer is correct. They're both positive. I am good. Question. All right, let's see here. A couple more, 2 more examples. So this next example, right? So let's use, you could do the properties of logarithms. Yeah, you could do the properties of logarithms here, but then you could also just look at this last one, right? If a log was equal to a log, I could do that here and then just get rid of everything. So if I add the natural log of 5x minus 10 to both sides, you get the natural log of 4 plus 5x equals the natural log of 5x minus 10. And I just showed you that you could just get rid of the natural logs because they're equal to each other. So you have 4 plus 5x equals 5x minus 10 and solve. So what's interesting here is if I subtract 5x, I get 4 equals negative 10, which is not true. So this is, there's no solutions here. Because 4 equaling negative 10, that's not, there's no solution there. No such thing. These two natural logs don't intersect with each other. And then the last one, I have 3 logarithms here. The easiest way to deal with this is to get them all on one side and then use properties of logarithms. So I'm going to subtract 2 natural log of x. So I have 0 equals natural log of 2x minus 3 plus the natural log of x minus 2 minus 2 natural log of x. Now, hopefully you remember, this can go here, and that's really minus the natural log of x squared. And I can put these all together now, write them as one single logarithm. So I have 0 equals the natural log of 2x minus 3 times x minus 2, all divided by x squared. Because this minus here means it's going to go in my denominator. Now I have one single logarithm. I'm going to rewrite it as an exponential. So I have e to the 0 equals 2x minus 3 times x minus 2, that's 2x squared, minus 4x minus 3x plus 6 all over x squared. Anything to the 0 power is 1, so e to the 0 is 1 equals 2x squared minus 4x minus 3x is 7x minus 7x plus 6 all over x squared. Multiply both sides by x squared. So you have x squared equals 2x squared minus 7x plus 6. I have a quadratic here, so I know I'm going to have to set it equal to 0 and solve. So I have 0 equals x squared minus 7x plus 6. Ideally, I do this by factoring. So the two numbers that multiply to positive 6 and add to negative 7 are negative 6 and negative 1. So my answers are 6 and 1, but I'll bet one of those is extraneous. So if I go up here, let's see, if I plug in 6, I'd be okay. If I plugged in 1 here, I'd be okay. If I plugged in 6 here to this next one, 2 times 6 is 12, minus 3 is 9. If I plugged in 1, I would have 2 times 1 is 2, minus 3, which is negative 1. So 1 does not work. Let's make sure 6 works on the end. 6 minus 2 is 4. So that would be fine. So my answer here is 4. Or sorry, 6. My answer is 6. So your homework tonight is worksheet 2 on GoFormative.